So in our last class, we discussed about mostly graphs, paths, cycle, and then we discussed about Eulerian graphs, Eulerian circuit or line, and solved few problems. Okay, and we have found the necessary and sufficient condition for a graph to have this Hamiltonian cycle or circuit or path that we already discussed. In this class, we are going to solve again a very interesting problem that's known as Hamiltonian path or Hamiltonian circuit. But before going into that, let us first try to solve a puzzle. Okay, it's a combinatorial problem. It says that nine members, can you see this? Yeah, it says that nine members of a new club meet each day for lunch at a round table. So suppose we have nine members, 1 to 9, and this nine member is a new club. That's why nine members of a new club met each day for lunch at a round table. They decide to sit such that every member has different neighbors at each lunch. That means, suppose day one, suppose uh, somebody, this is the arrangement. So this is the first. So this is the first participant or first guy, and suppose his neighborhood is 9 and 2. Okay. So next day, when they are going to sit, they have decided that for one, for the friend or for the participant one, the member one, 9 and 2 will not be there. That means in the next day, the neighborhood of 1 cannot be 9 or 2. That means maybe 8 and 3 and so on. Okay. So the question is, how many days can they arrange, can this arrangement last? That means if they want to continue with this process, maximum how many days that they can continue, so that each member will have different neighbors. So each member will have two different members as neighbor. So they will want two different members each day. So how many days they can run it? Okay, for a simple, if you look at it in a very simple way, then you can see that day one, for the first one, first member, 9 and 2 were the uh, neighbors, and maybe for the day two, 8 and 3 may be the neighbors for day 2, and so on. So the question is how many days that they can last, or this kind of arrangement last for how many days maximum. So any hints or any guess? So in all your arrangement, uh, you need to have basically all the members present, and you want. So maybe for the first day arrangement, you can think like that. Once one is there, his neighbor is 2 and 9. So you need to give a kind of arrangement. For example, so this is one arrangement: 1, 2, 3, 4, 5, 6, 7, 8, and 9. So this is one arrangement: 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1 maybe. And maybe another arrangement could be like this, say 1, 1, 2, like this, 1, 3, 1, 3, then maybe 5, then from 5 maybe 6, or you cannot have 6 here, so you need to check another thing. Okay, let's see, let's move through this. So 1, 3, 1, like this. I can take 1 goes to 3, 3 goes to 5, then maybe 5 goes to 2. Yes, I can come here 2, and from 2 to 7, and then from 7 to 4, and then 4 to 9, and 9 to 6, and then 6 to 8, and then 8 to 1. So now you can see that it starts from 1 and it ends at 1. So all the remaining, so here second is second participant is there, third participant is there, fourth, 5, 6, 6 is there, 7, 7 is also there, 8 and 9. So all the 1 to 9, all the members are exhausted. And if you make an arrangement like this, so 1, 3. So just beside 1, you will have 1 and 3. So that means for 1, the two neighbors are 3 and 8. So they are the neighbors of 1. So from the graph, it's clear. For 1, the neighbors are here. For 1, the neighbors are 8 and 3. Similarly, for 2, the neighbors are 5 and 7. So previously for 2, it was 1 and 3. But now for 2, it's 5 and 7. So you can see that these two arrangements are there. That means this arrangement can be last for 2 days. Now if you can find such kind of arrangement, then it will go further one more day, then maybe one more day. Now the question is, how many days will that be continued? So that's the question. Okay, that's a some combinatorial problem that you can solve in many ways. In this class, we are basically going to solve this kind of problem using graph theoretic technique. And what I will basically do is basically will tend to solve this problem. But before that, we are going to define few of the statements or few of the definitions, and that will help us in solving this problem. Okay, so let us go to this Hamiltonian path and Hamiltonian circuit. So this topic is very important. So first, what is the definition of Hamiltonian path or Hamiltonian circuit? So we have already seen this Eulerian line. So what is that Eulerian line? If you go like this, suppose you have few vertices, say 4 vertices maybe, and suppose this is your graph. Suppose so okay, so 1 2 3 4 1 2 3 4. Suppose this is my graph, so it has 4 vertices and few edges. Okay, say if I name these vertices as v1, v2, v3 and v4. So I need to uh, solve this problem. Like suppose you started from any of these vertex. For example, suppose you start from this. You need to explore all the edges exactly once, and you need to come back to this position once again. And you cannot lift your pen from the paper. That means you should start from here, you should explore all the edges exactly once, and you should come back to V1 once again. So that's the point. So how to do that? There could be many ways to solve this problem. So one of this solving could be like you start from here and you first go here, then come here, then come here, then go here, then go here, and then go here. So you can see that all the edges are explored exactly once, and that is known as Eulerian circuit or Eulerian line. So in some of the authors they tell it Eulerian circuit. Some of this in this book, in Narsingh Dev's book, it says that Eulerian line. Now, as we have seen already that the necessary sufficient condition for a graph to have this Eulerian circuit or line is that the degree of each vertex must be even. So it's a connected graph, and you see that this the degree of each graph. So I'm talking about only connected graphs. So here the degree of this vertex is 1, 2, 3, and 4. This vertex is 1, 2, 3, and 4, and this vertex are all 2. So degree of each vertices, if the degree of each vertices in a connected graph is even, then you will certainly have an an Eulerian line. And conversely, if you have an Eulerian line, then suddenly the degree of each vertices must be even. So that was a kind of, so that has to be a connected graph. So for a connected graph, you will have a necessary sufficient condition for a connected graph to have Hamiltonian circuit or Hamiltonian line. So that's already done. We have already seen. Now we are going to explore it in a different way, where here the number of edges is not that important, but here what we need to do, we need to suppose we start from here, we want to come back here, but previously what we had a target was to explore all the edges exactly once, but here the target is only to explore the vertices exactly once. Okay, so if you want to consider this for a circuit, then you need to come back to this vertex again. That means you need to start from a vertex and you should come back to that vertex by exploring all the vertices exactly once, except for this initial or end vertex, because you need to come back here once again. That's why if this kind of tracking process is there, then we call it Hamiltonian circuit. So if I go for a definition here, it says that a Hamiltonian circuit is a in a connected graph is defined as a closed work. That means you should start from one place and you should come back to that same place, that traverse every vertex of G exactly once, except of course the starting vertex at which the work also terminates. That means from a starting vertex and end vertex, except for that vertex, you need to explore all the vertices exactly once. So that's the idea of Hamiltonian circuit. So let us try to make a path here. Suppose here we start with say some vertices, say v1, v2, v3, v4, and say v5, v6, v7, v8. Okay, so there are 8 vertices. Now I need to check whether we can have a Hamiltonian circuit within it or not. Okay, so suppose start with this vertex. So start with this vertex v0. Okay, so now suppose I have the edge e1, e2, say e3, e4, e5, e6, e7, e8, then e9, e10, e11, e12. Now somebody, can you please give me which would be the one of the Hamiltonian circuit? Travel through this like this. If you travel through this, first come here, then come here, then come here, then come here, then go to this, and then go to this, go to this, and then come back here. So if you travel through this, then you can understand that you can explore all the edges, but suddenly few of these edges like this edge, this edge, this edge are not explored. So you cannot say that this is a this is an Eulerian circuit or line, because you are unable to trace this edges. And you can see that the degree of these vertices is 3. This is also 3. So it can never be an Eulerian line. You can never find an Eulerian line or circuit here, but here you can find certainly an Eulerian the Hamiltonian circuit. Okay, let us try to solve this one. Make it little larger, then it would be easier. Okay, okay. So let me Yes. So let us try to find here. So here also you can see that there are many vertices are here, and you need to. So it's already given. So start with something here, then go back here, 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 then come here, then this, then this, and then this. So you can see that you are exploring all the vertices exactly once, but there are few of these edges are left. Now if I ask you this question, so this is a Hamiltonian circuit. So if I ask you a question, uh, suppose a connected graph G contains n vertices and a Hamiltonian circuit, then this circuit contains dash many edges. Can you tell me how many edges? What would be how many edges? Fill in the blanks. Vertices, then how many edges that it should contain? Any idea? Quickly. Anybody? How many? Okay, Akash.
Sir, I need to get some.
Okay, try it. Just have a look at this image.
Sir, is it
Yes,
the same number of vertices as the number of vertices and the number of edges will be same?
exactly. So here with, if this will have a Hamiltonian circuit, then the number of edges in that Hamiltonian circuit will be exactly n. So the length of this circuit will be n. So how many edges that it will contain? Okay. So that's just an observation. Okay. So I think the definition is quite clear to all of you. Now, can you tell me that if a graph is connected, will that graph will always contain a Hamiltonian circuit? Suppose a graph is connected, will that graph be always contain an Hamiltonian circuit? Can you give an example of a graph which does not have any Hamiltonian circuit? Is the question clear? So question is, give an example of a connected graph having no Hamiltonian circuit. Is the question clear? Can you give an example of a graph which does not have a Hamiltonian circuit?
Sir, a graph with a vertex of degree 1 cannot have a Hamiltonian circuit.
Okay, for degree 1, so like this, how can you have the vertex, only one vertex with like this? How can you have a graph with only one vertex and degree 1? Are you talking about this or only one vertex?
No, no, sir. I told that. A graph with a vertex that have of degree 1.
So this is degree
Yes,
1, this is
first
degree
one
1.
is correct.
Yeah. So you say that this is an Hamiltonian, is not an Hamiltonian, is not an Hamiltonian circuit, right?
Sir, Kolpuk, sorry to interrupt you, but Kolpuk has returned home, so can he join the class right now?
Yeah, he can. Yes, sure.
He's asking for that. Okay, thank you, sir.
Okay. So what he says that any connected graph having a degree 1 vertex, then it will not be possible to have a Hamiltonian circuit. For example, suppose I have this. Okay. If I have this, then will it be possible to come back here? Suppose start with this. If you go somewhere, say here and then here and then here, then you will not have any opportunity to come back here without exploring any of this path. So if you are exploring any of this edge, then certainly the vertices will be repeated more than once except for this. So if a graph will have a connected graph having a vertex, of course, if with degree 1, then suddenly you cannot have this Hamiltonian circuit. So okay, so you can understand that a graph may not have a Hamiltonian circuit. So just let me remind you what is Hamiltonian circuit. So Hamiltonian circuit is, let me start from here. So Hamiltonian circuit means uh, a Hamiltonian circuit in a connected graph is defined as a closed work that travels through every vertex of G exactly once, except, of course, the starting vertex at which the work also terminates. That means you need to explore all the vertices exactly once, and you need to come back to the vertex from which you started your journey. So that's all. So for example, here, if you look at here, so if you start from here, then you just go back like this, and come back here, exploring all the vertices exactly once. Unlike the Eulerian circuit or Eulerian line. So there you have to explore all the edges exactly once. But here the idea is you need to explore all the vertices exactly once. Okay, and you need to come back to the original position from where you started your journey. So that's the question, and the question that I just asked here was if so, will all the graphs, connected graphs, have this Eulerian circuit? The answer is of course no. For example, if you have this kind of graph, then suppose you started from here, then if you go here, here, and here, you will not have any edge to come back here without repeating the vertices. That's why it will not have a Hamiltonian circuit. Okay, so now you can reduce the definition. So why not we can have a Hamiltonian path? That means you may not need to come back to the original position like this, where just now Akash gave an example here where you understand that if you start from here, you will not have any edge to come back here. Okay, so let us dilute the definition. Let us remove some condition that you may not need to come back to the original position, but you need to explore all the vertices exactly once. So what you need in a connected graph, you start from some vertex, you explore all the vertices exactly once. Okay, so the condition that we discarded here is that you need not come back to your original position. That means if a graph will have Hamiltonian circuit, then suddenly if you remove any of one of the edges from that Hamiltonian circuit, then that will have this particular property. So we call this as Hamiltonian path. Hamiltonian path. Okay, that means it should not come back to the original position. So here you can understand that if V1, V2, V3 and V4 are the four vertices, then this explore how to explore this. Suppose you explore like this and this, then suddenly it will contain, this path will suddenly contain all the vertices of the graph exactly once. So that is known as Hamiltonian path. Okay. So here you can understand that this graph does not have an Hamiltonian circuit, but this graph will certainly have a Hamiltonian path. Okay. So in case of Eulerian circuit or Eulerian line, as I just now mentioned, that there is a necessary and sufficient condition for a connected graph to have, whether it's an Eulerian graph or not, it's very easy to find, because we just need to check whether the degree of each vertices is even or not. But unfortunately, it's not yet proved, or nobody yet found any of the necessary sufficient condition for a connected graph to be Hamiltonian or not. That means whether it will contain a Hamiltonian path or not, no necessary and sufficient conditions are yet been found. So it's still an open problem. So you can start thinking about any of such conditions, then suddenly you will get some good award with respect to mathematics. So it's still an open problem. The statement is very easy. So check whether a graph is Hamiltonian or not. That means whether it contains a Hamiltonian circuit or not. So you need to give some condition, so that this condition should be necessary as well as sufficient. So some sufficient conditions are available. A sufficient condition for a complete graph G to have Hamiltonian circuit is that the degree of every vertex in G is at least n by 2, where n is the number of vertices. So this is sufficient condition, not necessary. So this, if somebody is interested to have a look at this proof, so he or she may have a look at this reference, and they will get the reference or the proof of this theorem. But as I mentioned, this is only the sufficient part, and the necessary part is yet to be proved. So if you are able to prove this, then you will certainly be famous, no doubt about that. So it's a long-standing problem, as I have mentioned, it's 1859 or something. So when Hamilton actually proposed this problem, so it's a long-standing problem. So if I request all of you to have a look at this. So you'll be surprised to know that many of the combinatorial problems that are not being solved for many years are being solved by very young mathematicians, mostly the students, because they are very fresh mind students and they can think. And if you know many things, then you are always trying to involve the complex mathematics inside it, but sometimes very tricky argument comes into mind, and that actually solves many of such problems. So I think you can also have a try of some necessary and sufficient condition for a graph to be Hamiltonian or not. Okay, so as I just mentioned, so this is the Hamiltonian path. So Hamiltonian path, it says that if we remove one edge from Hamiltonian circuit, we are left with a path. This path is called Hamiltonian path. Clearly, a Hamiltonian path in a graph G traverses every vertex of G. Since a Hamiltonian path is a subgraph of a Hamiltonian circuit, which in turn is a subgraph of another graph, every graph that has a Hamiltonian circuit also has a Hamiltonian path. Just now I have mentioned. There are, however, many graphs with Hamiltonian path that have no Hamiltonian circuits. For example, just now I have mentioned here, this is an example of it has Hamiltonian path Hamiltonian path, but no Hamiltonian circuit. Hamiltonian circuit. So you may find many such examples. Okay. Okay. So let us now try to. Can you just try to find some of the Hamiltonian path here? Let's see. Let us do it here. Maybe. Okay. For example, this. Let us try to this. Okay. Okay. So let us try to find Hamiltonian path here or circuit here. So let's take this V1, E1, V2, E2, V3, V3, V4, V4, V5, E5, V6, E6. Let's E7, V how much? V7, then E8, V8, E9, V9, then E10, V10, E11, V11, E12, V12, then E13, say E14, V how much? V11,
13.
V13, say E15, V14, E say V15, E16, E17, E18, say V16, then E19, E20. Hopefully that is done. So can you find some of this?
Yes, sir. I find a path.
Okay,
Hamiltonian
you
path.
find a and circuit.
No, sir. I can't find any circuit.
Okay, so tell me this path.
Sir, first
Okay,
start V11 to V3.
V11. Where is V11? V11 is in a which circle? Inside circle? Yes,
Left side, sir.
yes.
Sir, left
Okay,
side.
this
Yes.
one. Yes. Okay, from here to
V3,
V3,
V12.
V12. Where is V12?
Sir, no, sir.
No,
V2. I
no.
think it is
2,
V2.
V12. Yes, V2.
Sir, V2 to
Yes,
V12.
V2 to V12,
Sir, V7,
V7,
V1.
V1,
Sir, then V6,
V6,
then V8. Oh, sir, sorry,
V8,
sorry, sir. 1 second. Ah, yes, yes, sir. V8, then V9,
V9,
then V5,
V5,
then V4,
V4,
then V10.
V10.
Then I think it is V15,
Okay.
then V14,
Yes.
V16, um,
V16.
16, and then V again V12.
No, you cannot repeat. You
Oh,
cannot go to V12.
so I think I get a Eulerian path.
No, you. It's difficult
No,
to
no,
get
no,
an
no, no.
Eulerian
Yes,
path. You
yes, yes,
cannot
yes,
get.
yes. Sorry, sorry.
Yes.
Yes, 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 yes.
Okay. Anybody will try something? Okay. Anyway, you can always try, but it says that it does not have any Hamiltonian circuit. So as you understand, if it will not have any Hamiltonian circuit, then it will certainly will not have uh, Hamiltonian path, because if you remove any one of the edge from that Hamiltonian circuit, you will certainly end up with an Hamiltonian path. So certainly, according to this book, it says that it does not have any Hamiltonian circuit or path. Similarly, this see graphs without Hamiltonian circuit. So here also this graph will not have Hamiltonian path. So you can see that this graph has a special property. The degree of each vertex is 3, right? You can see, no, not each vertex. So here this degree is not 5. So not, yeah, okay. So there are few graphs where the degree of each vertex is exactly the same. So these graphs are called regular graphs, but this is not a regular graph, of course. So, but there are graphs where the degree of each vertex is exactly the same. These graphs are called regular graphs. But of course, this is not a regular graph. Okay. In my last class, I have already mentioned about complete graphs. I hope you remember complete graph. Complete graph. Complete graph means suppose you have, suppose, 4 or 5 vertices. You need to construct a graph such that if you take any two vertices, then there must be an edge between these two vertices. That graph is known as complete graph. That means if you consider all the vertices, then suddenly all the vertices will be connected like this. Suppose you take any vertex this, then you will suddenly find an edge between any other vertex. See, this vertex is connected with this vertex is connected with this and this. So take any of such vertex, then you will able to find that there must be an edge with any other vertex. So this is known as complete graph. So in case of complete graph, so the question is how many edges are there? In our last class, we have already discussed about it. So how many edges are there? If E is the edge set of this graph, then order of E is equal to how much? In our last class, we have,
Sir,
suppose we had,
NC2.
yes, suppose we had n vertices, then the number of vertices were nc2, and that is nothing but n into n minus 1 by 2. For example, here n is 5, so you can see that n choose 2 must be 5 into 4 by 2, that is 10. So you can see that the 10 count could be like this: 1, 2, 3, 4, 5, then 6, 7, 8, 9, and where is the other one? This, okay, this one, yeah, 10. So all this, so it will have exactly 10 edges with 5 vertices. So that is known as complete graph. Now try to understand about the problem that I mentioned as our puzzle. So what is that problem? The problem was seating arrangement problem. We come back to here. Here is again I am stating the same problem. 9 members in a new club meet each day for lunch at a round table. They decide to sit in such a way that every member has different neighbors at each lunch. How many days can this arrangement last? So for example, suppose here first member is sitting on the first day. On the first day, his neighbors are 9 and 2. In the next day, both 9 and 2 are not eligible to sit beside the member 1. So the question is, here we have seen already two of such arrangement. That means you may be it may be the arrangement for day 1, it may be the arrangement for day 2, and so on. So the question is, how many days can it last, so that every member will have different neighbors on each and every day. So that was a combinatorial problem, and we are going to solve this problem by using graph theoretic technique. Now, any guess that you want to find from here, like the Hamiltonian path or Hamiltonian circuit we have already defined. So is it an Hamiltonian, this one is an Hamiltonian path, can you say? Or Hamiltonian circuit? So it says that 1, 2, 3, 4, 5, 6, 7, 8, 9, again 1. So this is a Hamiltonian circuit. Now let's see whether this one 1, 3, 5, 2, 7, 4, 9, 6, 8, again 1. This is also an Hamiltonian circuit. So what we are actually trying to find here? So to solve this problem, what we are actually trying to find? Can anybody guess?
Sir, the number of Hamiltonian circuits.
The number of Hamiltonian circuits. Okay, but if some Hamiltonian circuit will have this property, suppose here, I mean taking just an example, suppose 1, 2, and then suppose these two edges are common in both the Hamiltonian circuits. Will that be sufficient for you?
No,
Suppose
no,
you
sir.
have, by some means you get two Hamiltonian circuits in which these two edges are common in both the Hamiltonian circuits. Will that be fine for you to count? So you are almost done, but one extra term you need to add. What is that term? What extra term that you need to count? You are certainly counting the number of Hamiltonian circuits inside which kind of graph. That is also important. And second, you are also trying to count, because if you are going to count like this, then suddenly uh, one will have, in two of these circuits, one will have the same neighbors. That is not eligible. So what you want to actually count? So you remember edge disjoint? That means two of this Hamiltonian circuits should not have any common edge. See, both of them, they are basically edge disjoint. They do not have any common edge, right? And also, on what kind of graph we are trying to find this problem? We are actually trying to find for a complete graph with 9 vertices. So we are actually trying to count the number of edge disjoint Hamiltonian circuit in a complete graph with 9 vertices. So that's our aim. So if we are able to count that, then basically we are done. Okay. So that's the problem here. So we are actually trying to count the number of Hamiltonian circuits in a graph. Okay. So the determination of exact number of edge disjoint Hamiltonian circuit or path in a graph in a general is also an unsolved problem. So it's unsolved problem finding the exact number of edge disjoint Hamiltonian circuit in a graph, that means in arbitrary graph. Okay, but fortunately here we are actually solving, or we are trying to solve it for a particular kind of graph that is known as complete graph. And fortunately for this complete graph, the result is there. So in a complete graph, mind that in a complete graph with n vertices, there are n minus 1 by 2 edge disjoint Hamiltonian circuits. If n is odd, that is also important. If n is odd, then we can find it easily. So please try with when n is even. Okay. So we are actually trying to count the number of edge disjoint Hamiltonian circuits in a complete graph with n vertices where n is odd. For our example, the value of n was 9. So we'll be happy. So, but this is much general formulation. So let us try to prove this. Okay. So as I mentioned, so it's the proof. A complete graph with n vertices has n C2 edges. Just now we have shown it. That means n into n minus 1 by 2 edges. And the Hamiltonian circuit in G consists of n edges. Just now we have also mentioned a Hamiltonian circuit. If we have an Hamiltonian circuit in a graph, then it must have n edges. Therefore, the number of edge disjoint Hamiltonian circuit in G cannot exceed this. See, this was n into n minus 1 by 2 edges, total number of edges, and in each of the Hamiltonian circuit, there are n edges. So, how many maximum, how many, uh, the number of edges? So, therefore, the number of edge disjoint Hamiltonian circuit in G cannot exceed this, because each of the Hamiltonian circuit will contain n edges, and there are this many edges. Okay, there are this many edges, and we want edge disjoint. So no edge will be common for any of the two Hamiltonian circuits. As a result, how many, just divided by n, that many number that it could have maximum, so cannot exceed n minus 1 by 2 many Hamiltonian circuit. So it cannot exceed, that is important. You may not have that many, but suddenly you cannot have more than this, because then otherwise you will have a shortage of edges, because this Hamiltonian circuit cannot exit this by n, that means n minus 1 by 2 such Hamiltonian circuits. Okay, now we are going to actually show that, okay, this many distinct edge disjoint Hamiltonian circuits are present in a complete graph. So this construction is very interesting. Okay, let us have a look at this. So try to draw a circle. Try to draw a circle with 1 as center. So I want to put n of such vertices on the periphery of the circle with 1 as a center, and say this is the midpoint of the straight line. So I put 1, then 2 here, and then n here. So this is now the midpoint. So I can think of this as a radius. Now, if I draw a circle with all the points on the periphery of that circle, then the placement of these points will be clear to all of you. Okay. So suppose this is my circle. Okay. Okay. So how I put this? So 1, then 2, then I put 3 here, and I just opposite to that I put 4. Then I go up to 5, and then opposite to this is 6. Suppose I have 7 here, then I put 8 here. Okay, and suppose I put uh, 7 here, then 8 here, I put 9 here, I put 10 here, I put 11 here. So n is odd, that means total 11 vertices are there. Now I can see that this is a Hamiltonian circuit. How? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and go back to 1. So it's an Hamiltonian circuit. Now you can understand that all these angles, this angle is basically fixed. So you can place it symmetrically, because on the upper half of the triangle of the circle, I have given 1, 2, 3, 4, 5, 6. 6 of the vertices are on the upper half. And again, if I consider 2 and 11 together, then 1, 2, 3, 4, 5, and 6. 6 vertices are on the lower half, including this 2 or 11. So you can understand that this angle is basically, you can make it a fix. You can choose this angle so that they can be placed symmetrically. Okay, so here, though this angle looks quite big, but you can place it, of course, symmetrically, so that this angle is fixed. Now, can anybody be able to tell me what could be this angle? What could be this angle? This angle could be total 360 divided by n minus 1. That means 10. Okay. So, if you consider this angle to be n minus 1 360 by n minus 1, then you will have 36-degree angle. Okay. So first make a rotation of this 360-degree angle. For example, suppose I have, if I go back to my original problem of seating problem for that club, so there we had 9 participants or 9 members. So how I put it? So 1, I put it 2 here, I put it 3 here, I put it 4 here, I put it 5 here, 6 here, I put it 7 here, I put it 8 here, I put it 9 here. Okay. So this angle has to be done in a better way. I couldn't draw it properly. So that this angle should be the same angle. This angle and this angle should be the same. So like this, and then this angle will also be the same. Okay. What is that angle? This is nothing but the, so here we have 360 divided by 8. So that could be this angle measurement. So initially, the first Hamiltonian circuit for me was 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 1. Okay, I come back to here. Now, if I do a trick here, for example, if I just make an angle shift here, rotate here by 3 by 36-degree, then what will happen? This 4 will come here. So here it will be 4, it will be 2, this will be 3, this will be 5, this will be 7, this will be 9, this will be 8, and this will be 6. Now if I make the same pattern, like 1 goes to 4 first here, then come here, that means 2, then again come down, that means we have 6, then go up, that means we have 3, then go down, we have 8, then go up, we have 5, then come down, we have 9, and then again go back to 7, and from 7 you come to 1. So it starts with 1, ends with 1, excluding all the vertices exactly 1. So this is also a Hamiltonian circuit. This is also a Hamiltonian circuit. So, and most interestingly, both of them, they are edge disjoint. So the question is, how many such you can make it? You can make it exactly n minus 1. So 360, sorry, you will certainly make this how many? If you calculate it here, you can see that. So you can first make it 360 divided by n minus 1. In my last class for 9 case, it was 360 divided by 8. Then you rotate it by 2 into 360 divided by 8. Then rotate it by 3 into 360 divided by 8, and so on. And it will continue till n minus 3 by 2 into 360 by this degree. So altogether, how many such you will have? It starts from, if you can count this 1, 2, 3, and n minus 3 by 2, then there are this many rotations. Remember, you started with the initial phase where 1, 2, 3. That means here the rotation was 0. So along with this many, there will be one more. So altogether, you will have n minus 1 by too many such circuits. So that's the proof of this. The number of edge disjoint Eulerian, sorry, Hamiltonian circuits will be n minus 1 by 2, and all of them are edge disjoint. That is very important. And that is what we want to find in case of this seating arrangement problem. So I have already given you two of them. So you can understand that there will be n minus 1 by 2 many such path disjoint Hamiltonian circuits, and that will be basically for n equal to 9, that will be basically 4 for n equal to 9. That's why I have already given you two of them. So you need to give me the remaining two more Hamiltonian circuits so that you can easily calculate. But the most interesting part here is that there are huge application in real life. So there is a problem called traveling salesman problem. So let me try to explain. Suppose suppose there are four cities. Suppose we have four cities. Say this is Delhi. Suppose this is Mumbai. Say this is Chennai, and say this is Kolkata. And suppose the cost of traveling from here to here, say by car or by flare, is something, say 10,000 and maybe 10,500. Say this way and this way. And say there may be three paths like this, or maybe this. And there are some cost here. Say suppose from Delhi to Kolkata, there is only one path. There is a only by flight the company can afford, and say by road, say like this, some cost. Say this is 7,000, and then from here to there, and then from here to there. So now you can understand this is a kind of complete graph, or maybe you might have some more options. You can also take a car from here to there. You may go by train as well. You can also take a boat from here to somewhere. There are many ways that you can define. The idea is, suppose one salesman, so the name is traveling salesman problem, TSP. It's famous problem. It's an optimization problem. So it says that suppose one salesman wants to travel through all the cities exactly once. He may start from a particular, for example, he may start from Delhi and he wants to come back to Delhi by exploring all the cities exactly once, such that the cost of his travel is minimum. Okay. So the point is, he needs to find the cost in such a way that he will be able to explore all the cities exactly once, and he will start from Delhi and come back to Delhi, but the cost of traveling will be minimum. Okay, so that's the idea of traveling salesman problem. And this graph, now you can understand that you can shift this graph in shift the whole problem in terms of graphs with vertices and then edges with some number. These numbers are called weights on the edge. So now this graph becomes weighted graph. Okay, and in that weighted graph we are basically trying to find kind of the Hamiltonian circuits that will have the minimum cost. Okay, so that's known as traveling salesman problem, and it has lots of application in many ways for companies to run the business and all. Okay, so what I try to mention here is that this necessary sufficient part is very important here, because nobody could yet find out the proof of a necessary or a condition for a necessary and sufficient condition for a graph, connected graph, to be Hamiltonian. So I encourage you to try to have a look at this problem. And sometimes it happened in the mathematics, in the world of mathematics, that many of such combinatorial problem could be solved by young mathematicians who do not have much exposure on many results. Sometimes it happens that if you know many of such results, you are always trying to incorporate those results inside your techniques. So without that technique, since they are quite tricky, you may be able to solve this problem, and I have every wishes to all of you. So please try it and try to solve this problem. Okay, so that's all. If any question, or if you have any question, you are free to ask.